Now I'd like to give you one very useful representation of the gamma function. It's called the Hankel representation. Let's consider the following integral, taking along the loop contour depicted in the figure. The contour itself is called the Hankel contour. So why such unusual contour? Doesn't the integral cancel when going along the symmetric contour back and forth to minus infinity? It does, but only when the integrand is single-valued. The point here is that the integrand contains t to minus z, which is a multi-valued function. T equals 0 serves as a branch point. To define the function uniquely, we need to draw a branch cut and fix the regular branch. So we place a branch cut in such a way that it doesn't cross the path of the contour, namely along the left real semi-axis. We fix the regular branch by the condition that function t to minus z is positive for positive t. So basically, the argument of t is said to be negative pi at the lower bank of the branch cut and pi at the upper bank. The exact shape of the contour is quite arbitrary. The only essential detail is that it should circle around the branch point and have minus infinity as its start and end point. One thing you notice, the integral converges very well because of the exponential function and the fact that it starts and ends at minus infinity, where e to t vanishes. Also, the only possible singularity of the integrand is the origin. But the contour doesn't go near the origin. The loop can be stretched to become quite wide to avoid it. So the integral is well defined for any value of z. Thus, the only possible singularity of the function defined by that kind of integral is z equals infinity. Otherwise, it's a regular function in the entire complex plane. Now we use another very efficient technique of computing the integral along the loop contour. We shrink the contour to facilitate the computation. We turn it into the combination of two straight lines along the negative real semi-axis and an infinitesimal circle. The radius of a circle is taken to be some infinitesimal epsilon, where epsilon tends to 0 at the end of the calculation. The vicinity of the origin leads to the divergent integral in case when real part of z is greater than 1. Indeed, it's the case very similar to gamma function. The vicinity of the origin leads to the divergent integral in case when real part of z is greater than 1. In the vicinity of the origin, we can change the exponential to 1, and the integrand becomes t to minus z. We rewrite and obtain the following result. So the thing diverges when real part of z is greater than 1. But we know that the function I of z is regular at any finite z. This superfluous divergency comes from the deformation of the contour, which shrinks it to the vicinity of a branch point. And the answer shouldn't depend on the contour deformation. So when computing the integral, we assume that real part of z is smaller than 1, and the integral is going to converge. But the answer will hold for all finite z. And this assumption should be lifted at the end of the calculation. Let's now do the calculation. First, let's work it out along the lower bank of the branch cut. The argument of t is negative pi, and as a result, we introduce the natural parameterization of the contour. T equals to rho times e to minus I pi, where rho is the modulus of the complex number. It changes from plus infinity to epsilon as we go along the contour. So we plug in our parameterization to the lower bank part of the integral, and it is transformed like this. Now, if real part of z is smaller than 1, the integral converges at the upper limit, and we can take the limit epsilon tending to 0. Finally, we have the integral. Changing e to minus I pi to minus 1, and interchanging the limits of integration, we arrive at the following expression. We can also put the constant e to I pi z factor in front of the integral. So what is left under the sign of the integral is now very recognizable. It's simply the integral representing the gamma function of 1 minus z. So now we get the answer for the lower bank integral. In the same spirit, we compute the integral along the upper bank of the branch cut. The only difference is going to be the change of the argument of the complex number t. It used to be negative pi, and it will become pi. The parameterization of the contour will be simply t equals rho times e to I pi. The rho parameter this time will change from epsilon to plus infinity. Everything else is going to be the same. So the answer is the same gamma function with slightly altered coefficient. Notice the minus sign due to the opposite direction of the integration. Finally, there is the integral along the small circle of infinitesimal radius epsilon. Let's analyze it. To compute it, we introduce the obvious parameterization t equals epsilon times e to I phi, where phi changes from minus pi to pi. The t differential is now dt equals I epsilon e to I phi d phi. Since the modulus of t is infinitesimal, it's simply equal to epsilon. In the integral, we substitute the exponential with 1, and the integral is turned into a simplified one over the angle phi. The crucial thing is that we can factor out epsilon to 1 minus z. And this is precisely the factor which defines the order of magnitude of the integral. The remaining integral is a simple exponential, but the important thing is that it's some finite number. So the integral along this circle is proportional to epsilon to 1 minus z. So when condition real part of z is smaller than 1 holds, the integral along the small circle can be discarded. And now we are left with just the two gamma functions. So the integral along the contour is reduced to the integral along the upper bank and the lower bank. Factoring out gamma function, we see that expression in brackets is nothing but a sine function of pi z times 2i. Dividing by 2 pi I, we obtain the I of z function. But now we use the mirror relation. We see that the right-hand side function arranges itself into a simple 1 over gamma function of z. And so we've just established the desired Hankel representation of the gamma function. As we remember, this result was derived under the assumption real part of z is smaller than 1, but of course it holds for any finite z.